I'm going to show you how to use Google Drawings to take a motion diagram and get velocities and accelerations. So I have here a motion diagram which shows the position of a ball rolling up an incline at equally spaced intervals. I can label this with displacements. So the displacements between time 0 and time 1 is found by just drawing a vector between those points. And I can label that as x01. And I'd like the 01 to be a subscript, so I will just highlight the 01, go to Format, Text, Subscript. All right. One nice thing about Google Drawing is that if you click on an object, it can tell you the geometry of it. And if you're not seeing this box on the right, you could just click on, so if I close that, if I click on Format Object, it appears. And in particular, it tells us the width and height of the box that contains this arrow. Well, the width is nothing but this length. The height is nothing but this length. So that width and height correspond to the components of this vector. So this vector has an x component of 3.28 inches and a y component of 0.87 inches. So I can add that to my label. This displacement should correspond to the average velocity during this time interval times the length of the time interval. I'd like to call the time interval delta t. So I can insert the character delta by going to Special Characters. And I just type into the search box delta. I can then repeat this labeling for all the other time intervals. So if I'm told how large delta t is, I know the velocities at each of these time intervals. And this is exactly what we were doing in our spreadsheets to take numerical data and turn it into numerical data for positions and turn it into velocity data. All right. And as with what we do on the spreadsheets, we can then combine the differences of velocity vectors to get accelerations. So I can take this vector here and copy it, bring it down here. And the next displacement vector, I can copy it and bring it down. The difference between those two vectors, graphically, just corresponds to that vector there. This thing is x 2 minus x01. Now, the signs are always tricky on these things. The way I always remember it is if I take x01, which is the long vector here, and add this new black vector, I get to the blue vector. So this thing is x12 minus x01. Okay? And that should be equal to the difference in velocities times the time. Okay. Now we can use one more relationship, which is that the change in velocities is given by the acceleration times the change in time. Okay. So v12 is the velocity during this time interval. v01 is the interval during the previous time interval. So this should give me roughly the acceleration at time 1. Well, we can copy that vector and put that up here. And we can either use graphically what the components of that acceleration vector are, or we can use these components and subtract them to get the numerical expression for the components of the acceleration. Right? We can repeat this procedure with a different time interval. And the equivalent graphical construction should give us not the acceleration at time 1, but now the acceleration at time 2. And we see, for this simple case of this ball rolling up a hill, that the acceleration points parallel to the ramp. One also sees that the length of this vector looks very similar to the length of this vector. And indeed, the case of a ball rolling up the hill is typically well described by motion with constant acceleration. You will have lots of fun playing with this in your recitation section and in the homework.